Okay, awesome. So thanks for that kind introduction. As Steve said, I work at the Structures Research Center for the Florida Department of Transportation. And I've been here about 6 years now, and with the department for about 13 years. And the project I'm going to talk about today is an in-house research project that we did that is, really a continuation of some work that FHWA did, but it's looking at large diameter reinforcing bars spliced in UHPC. So in Florida, we have a problem with corrosion in our substructures, and that's a problem that is different than a lot of other states where they have more of a corrosion problem in their superstructures. And so we, in our consideration of the use of UHPC, we want to use it where it's most appropriate. And for us, that is in the substructures where we do use large diameter bars. And so this research was aimed at finding out the required development length so that we could then use it in the substructures. So it's a pretty simple test setup. What we did is we had a base slab that was 3 feet tall, and then we constructed a spliced region on that base slab that joined bars protruding from the base slab in UHPC to a test bar. And then we used a load cell in line with a hydraulic cylinder to basically pull that bar vertically until we saw failure of the bar or of the UHPC. So in total, we did 127 tests, so it was a pretty long testing program. We considered bar sizes from number 8 size up to number 11 size. We considered 3 different concrete covers, between 1.75 to 3.75. So that corresponds to the limiting cover that we allow for FDOT projects, along with a 1/4 inch construction tolerance. We tested multiple different bar spacings, both a contact bar spacing between the test bar and spliced bar, a 6-inch center to center, and an 8.5-inch center to center bar spacing. Our embedment length, and splice length, which were iteratively determined during the testing program, the embedment length ranged from 8 to 13 times the bar diameter, and the splice length ranged from 6 to 11 times the bar diameter. And the method that we used to determine the required splice and embedment length for each bar size and concrete cover built on the previous tests conducted before the one we were about to perform. So here's some pictures and a video of our casting process. In general, for most of our tests, we placed the UHPC from one end and allowed it to flow along the length of the splice. We did do some tests where we instead did a random UHPC placement. And the purpose of that was to compare the splice performance with random fiber in the UHPC versus aligned fiber in the UHPC. So we had quite a lot of instrumentation on this small area of where the bar entered the UHPC. We had crack displacement gauges on each face of the UHPC surrounding the bar, and that's what you see as the labeled TML in the top left picture. In addition, we had 2 foil strain gauges on the bar, and we had a knife edge bracket attached to the bar with displacement gauges that measured the movement of the bar 3/4 inch above the top of the UHPC, and also measured the movement of the top layer of the UHPC as well. For material testing, we did, of course, compression cylinder tests, and we did the ASTM 1609 small beam tests. We did a few select direct tension tests, but that was only on I think, one set of UHPC castings. So that wasn't a common test for us. So the thing that we did that I thought was really interesting is we, during this testing program, we actually obtained a fiber optic sensing system. So how this works is a optical fiber is glued to the reinforcing bar, and it is able to tell us strain at 1/4 inch increments along the length of the bar, and it can be embedded in the UHPC. So using this system, we could actually gain a lot of understanding of what was going on within the UHPC when we pulled and tensioned that bar. So we saw several different modes of failure of the UHPC. We commonly saw cone failure, which is more common when you have a higher UHPC cover value. We saw a splitting type of failure, which is common when you have a low cover value, and then we frequently saw a combination of the two types of failures. So how we looked at our results to determine the required splice and embedment length is for each combination of bar size and concrete cover, we developed a graph that was the maximum bar stress achieved versus the concrete strength at the time of the test. And then similar to how FHWA did that work, we considered the bar to be fully developed if we achieved at least 75 KSI during the test. And we were targeting a concrete strength of 14 KSI because that is the concrete UHPC strength. It can feasibly be achieved after a 24 hours of curing. So that's what might be achieved for some of our accelerated bridge construction type projects. So using those two values, 75 KSI bar stress and the 14 KSI concrete strength, we could basically divide our graph for each bar size and concrete cover into 4 quadrants. And so when data fell within this one of the 4 quadrants, then that told us whether the embedment and splice length was sufficient or not. So when we have, say, the first quadrant on the top right of the graph, that's when the concrete strength exceeds 14 KSI and our maximum bar stress exceeds 75 KSI. But we don't know if that test proved that the embedment and splice length was sufficient because the concrete was too high to determine. But we do know that if the concrete strength is above 14 KSI and a bar stress is less than 75 KSI, then those parameters show a definite fail of the test. And that's what you see in the second quadrant on the lower right side. Now, when the concrete strength is below 14 KSI, but we still achieve the 75 KSI bar stress, that's really where we want our test results to be. That shows a definite pass and that the bar stress of at least 75 KSI could be achieved in 14 KSI concrete. So that's what's in the top left of the graph. And then the final quadrant in the bottom left shows a probable fail, but the level of certainty varies depending on where our data fell. So since this is an abbreviated presentation, I'm just going to show you an example of the data. This is for the number 11 bars and a side cover of 2.75 inches. And in the report we're producing for this, all of the data will be shown for all 4 bar sizes that we looked at and the 2 to 3 levels of cover for each bar size. So what this graph shows you, now I should go over what the data series means. In the data series, the first number is the embedment length in bar diameters. The second number is the splice length in bar diameters. And the third letter or number indicates the bar spacing. So that's either a 6 for a 6-inch center to center bar spacing or a C for a contact bar spacing. So what this graph shows us is that the data with a 9.4 dB or diameter of bar embedment length and a 7.5 dB or splice length in bar diameters, those tests, we have a probable fail because we have, while the concrete strength is below 14 KSI, we have two tests in that test series that did not achieve at least 75 KSI bar stress. So you see the one green dot and the one black dot that are in the lower left quadrant of the graph. Those show us a probable fail of that embedment and splice length. Whereas for when 11.3 dB of embedment length and 9.7 dB of splice length were provided, all of those data points, the orange and blue data is in the top left quadrant of the graph, which shows that in all of those tests, the embedment and splice length was sufficient. So we basically repeated this process for all of the different combinations of bar size and cover, and then developed our recommendations here. So until our report is finalized, I guess this is still a little bit preliminary, but all of the testing is completed. So this shows you the required embedment length in terms of bar diameter and splice length in terms of bar diameter for all of the different bar sizes and cover values. Now for the 8s, 9s, and 10 size bars, we only tested the 1.75 and 3.75 inch cover, and we only tested the intermediate 2.75 inch of cover for the number 11 bars because we were seeing quite a lot of spread in the required embedment and splice lengths for the two different outer cover values. So this shows you pretty much what would be expected. For our number 8 bars, our results agreed pretty well with what FHWA has published. And then as you go to increasing bar size, then the required embedment and splice length typically increases. And then when you go from low level of cover to higher level of cover, the required embedment and splice length decreases. So I did mention that we did random and oriented fiber placements, which means that we placed UHPC randomly along our joint, and then we also placed UHPC from one end and let it flow along the splice region. So what we found is that the fiber orientation for our test did not show a difference in behavior. So we saw the same behavior whether the fiber was placed from one end versus placed randomly. And what we think happened is that basically a random fiber orientation was achieved in both cases. And that's because we were using pretty large diameter bars in comparison to our side UHPC cover provided. So that the bars basically disturbed the flow of the fibers in the UHPC, or disturbed the UHPC enough that the fibers became random. And so effectively we had a random fiber placement for both of our placement methods. And that was confirmed with some samples that we took out of the UHPC. So here's some of the data that we got from our fiber optic strain sensors. So what you see on the bottom, the x-axis of the graph is the gauge number. So along the fiber sensing gauge, the gauge number is increasing as the embedment of the bar increases in UHPC. So the gray region is the exposed length of bar, and then the blue region is the embedded length of bar in UHPC. And Each different data series corresponds to a different level of microstrain in the free length of the bar. So basically from the bottom line, which is a blue color, to the top line, which is an orange color, those correspond to different points of time during the test when the load is going from a low load to an increasing load. So some things to notice is that the fiber optic is picking up the ribs of the bar, and that is the undulations that you see in the data series. As well, we have something that looks kind of like a bilinear graph. So on the free length of bar, we have a fairly constant strain if you disregard the undulations in the bar. And then at some point in the embedded portion of UHPC, the strain starts to decrease. And our gauge isn't effective throughout the whole length of the bar, so we don't go all the way to the end of the bar. But if you continue that line down at the same slope, your strain should go to 0 at about the end of the bar.
About 1 minute left, Christine.
Okay, so I'll wrap it up, but this is another way of showing the fiber optic data, and it shows that the series go from on the left side, that's the exposed length of bar, to the right side is the most deeply embedded portion of bar. So you have yield at multiple locations of the bar, but the yield happens at different deeply embedded portions of the bar as the load increases. So what that looks like is before yielding, we have a linear strain profile in the UHPC, which is what you see in the yellow diagram. And then after yielding, we have a bilinear profile. And then what we have at shallow embedments of the bar, we have strain that looks exactly like a normal free reinforcing bar test. And then at deeper embedments, we have not a yielding profile, basically. So here's what that looks like. The A graph is a normal free bar load to strain diagram. And then at deeper embedments, what you have is the UHPC contribution is the red arrows that you see. And so you have the combination of UHPC acting in addition to the bar acting to resist load. But I have my presentation posted online. If anyone wants to follow up, then my phone number and email address are here.
All right. Well, thank you very much.